It's my pleasure to introduce Davoud Cheraghi from Imperial College of London, who will tell us about analytic symmetries of parabolic and elliptic elements.
Thank you for the introduction. Good morning, good afternoon, and maybe good evening to some of you. I would like to thank the organizers for inviting me, giving me this opportunity to present this work here. So this talk is about orientation preserving circle diffeomorphisms. So this will be the main objects of the talk, at least for half of the talk. So for these objects, we know that there's this classic notion of a rotation number, which gives the average rate of rotation by iterates of f around the circle. So this combinatorial quantity gives a lot of information about the dynamics of f. So the classic result that I guess everyone sees very early in the theory of dynamical system is that if you have like enough regularity and this rotation number is an irrational number, then the map is topologically conjugate to a rigid rotation. So it's a rotation by the same value. So here's the circle, which I usually denote by T, and F is acting on the circle. So the theorem says that there exists a change of coordinate psi that makes the dynamics into a round, rotation. So let me take another copy of this picture. So it's basically the same thing that I've repeated on the right-hand side. And let me start with two arbitrary points Z and W on these circles. They are not necessarily the same. Of course, we can map them on their psi, and we obtain 2 points Z prime and W prime. And obviously, there exists a map from the circle to the circle, a translation, which sends Z prime to W prime. We can lift this translation under these maps psi and obtain a map upstairs, phi, which conjugates f to itself and maps z to w. So in other words, we have a for any z and w, there exists a change of coordinate, a homeomorphism, which conjugates f to itself, but also in particular, phi maps the orbit of z to orbit of w. Yeah. So in other words, at the topological level, there's a total symmetry of the dynamics of f on T. Yeah. So this is like embedded into the proof that when you take the orbit of z, as long as you know the rotation number, the orbit of z combinatorially does the same thing as the orbit of any other point. But this result says that we cannot distinguish at the topological level. We cannot distinguish the orbit of z from the orbit of any other point. Yes, this is because topological property is very weak. It cannot distinguish these different geometries of orbits. Yeah, so this becomes a bit more interesting if we look for phis that are of higher regularity. Okay. So this is a huge topic. The problem of how you can go from some information about the regularity of f to information about the regularity of the conjugacy psi. Yes. I will just mention two main results in this direction. But as I say, there is like a huge theory factor. So the first one that I would like to mention is for smooth maps. So it's a result of Hermann that says, if f is a C infinity diffeomorphism and the rotation number satisfies a Diophantine condition, then the map is C infinity conjugate to the rigid rotation. And the second result is very similar. So it's by Yokos, which says that there exists a full measure set of rotation numbers H, such that every analytic diffeomorphism of the circle with rotation number in the class H is analytically conjugate to the rigid rotation, or with the same rotation number. So these conditions are optimal. So here optimal means that, if the rotation number is not satisfied, then there exists a map, there exists at least one map that is not C infinity conjugate to the rotation. And the same result is here. So if you have a row that is not of class H, there exists at least one map with that rotation number, which is not analytically conjugate to rigid rotation. So going back to my previous picture, so when we do have these rotation conditions, these arithmetic conditions on the rotation, we do have this, C infinity or C omega conjugacy to the rigid rotation. And I can repeat the same thing as I did in the previous slide and say that for any Z and any W, there exists a map phi which sends, Z to W. Yeah, it's a conjugacy. So in other words, the orbit of Z under the iterates of F and the orbit of W under the iterates of F, they produce the same geometry. So they have the same geometry on the circle, modulo C infinity, or in this case, an analytic map. Yes. So this of course happens when the map is conjugate to the rotation. What if the map is not linearizable? So if the map is not linearizable, if I take two arbitrary points Z and W, do they still generate the same orbits, up to C infinity or an analytic map? So in fact, one can move in the opposite direction. So linearizability means that the orbits generate the same geometries. The opposite of direction would be that if all distinct points produce orbits with the same geometries, up to say C omega map, an analytic map, then the map will be analytically conjugate to a rotation. Yeah? So, what I'm trying to say is that the presence of the amount of symmetries that you have in your dynamical system is a measure of the linearizability of the map that you start with. Yes. So I will make this a bit more precise. So as I said, a measure of linearizability or non-linearizability of a given map can be coded in the centralizer of that map. It's defined as follows. So if you have a map F of circle, it is, I've just focused on the C infinity and C omega case. So if F is S is one of these numbers, the centralizer of F is all diffeomorphisms of class S of T which commute with F. Okay. So this G plays the role of this phi that we have here. I don't even know why I used G. I could have used phi. So this is a class of diffeomorphisms of the circle. So it of course forms a group of under the composition law. One can also just consider the rotation numbers of these elements. So this is denoted by GS. Again, same style. S is either infinity or omega. So this is the rotation numbers of the elements that come from the centralizer. So anytime that G commutes with F, you take the rotation number of that G. So here are two comments. So of course, for every F, the iterates of F belong to the centralizer of F because the iterates commute with F. So they will be here. And if F is a CS diffeomorphism and it is CS linearizable, we saw that the symmetries or the rotation numbers of the symmetries is full. It takes every value. So this is what I have in this picture. So in the linearizable case, I can map any Z to any W by the same regularity as F. So the question is, what kind of sets can you get, in this form? So we see this example that, G is the full group. And in this case, the rotation numbers of f to the n's are n times alpha, n times rho, if the rho is the rotation number of f. So all the n times rows modulo z are contained in this set. It's a countable set. Yes. If this is going to be a measure of linearizability or non-linearizability, you want to take that black and white statement and see if you have intermediate maps with intermediate, linearizability in some sense. So that will boil down to, can I have maps such that these groups will take, not to be the trivial one here or the trivial one here. So there is a very strong restriction on the group G, which I try to explain here. So if F and G are two maps, two circle diffeomorphisms of some class, and one of them is linearizable, then the other one has to be also linearizable. So this is not too difficult to see, because you basically take the linearizing map for G, and the same map will also linearize F. So it's a simple lemma that everyone can do it. So this has a consequence. For example, if F is analytic and it is not linearizable, anything that commutes with F will not be linearizable. So that means anything that commutes with F, it cannot have a rotation number in the Hermann class. Okay. So G, the group G, lies outside in the complement of the class of Hermann numbers. So the class of Hermann numbers has a full measure set, but its complement is generic. So there's still plenty of room in the complement. And in the smooth category, you have a similar result. So if you have a map that is not linearizable, C infinity linearizable, the group is in the complement of the Diophantine numbers. And as I said before, how large can you make G for a non-linearizable map F? So within, this space or within that space. And second question is, are there maps with trivial centralizers? So if there are maps with trivial centralizers, these are going to be in some sense, the least linearizable maps. And as you know, even the group is very large, but it's not the trivial, full group. Those will be they are the closest to being linearizable, but not linearizable. So the two theorems that I mentioned about by Hermann and Yokos, they're remarkable results that they don't just answer the problem of linearization, but in fact they completely explain the geometry of the orbits on the circle. And they have these consequences about the group G. So in the C infinity category, there exists a map F. There exists a C infinity diffeomorphism with an uncountable group of symmetries. This comes from the work of Hermann. And again, for C infinity circle maps, there's an example with a trivial centralizer, and that is from the work of Yokos. So in the smooth case, we know much more than in the analytic case, because there's of course more flexibility when you want to build examples for C infinity maps. So in the analytic case, Yokos shows that there exists an analytic circle diffeomorphism such that the group of symmetries is uncountable. So this element is not, of course, maybe I should have written that this map is non-linearizable and the group is uncountable. And the question that was left open was whether there exists an analytic circle diffeomorphism that has a trivial centralizer. And we give an answer to this question. in a joint work with Arthur Avila and my PhD student, Alexandre Iliad. So I think I forgot to mention that everything that I'm talking about is a joint work with Arthur and Alexandre. So we show that there exists a map F, a circle diffeomorphism, such that the group is trivial. So that means the only maps that commute with F are iterates of F. So perhaps I should mention here that this theorem is not in the spirit of the results of Hermann and Yochoz. So Hermann and Yochoz give a very detailed description of the geometry of the orbits, and then these are byproducts of those results. But in our case, we don't explain the geometry of the orbits, even for the example that we built, but we come up with a way of building these examples in fact in a very explicit form that satisfies this property. So more precisely, our examples come from the standard family. This happens in mathematics. When you're looking for a counterexample, the one that you see that is around you almost all of the time, that is the answer. So you have seen this class of maps. So A and B are parameters, so real numbers. And this is a map from R to R, but it also commutes with the translation by 1. So it's a map of the circle. And the theorem that we actually prove is that for any value of B in the interval 0 to 1 over 2 pi, there exists A in R such that the centralizer of FAB is trivial and the rotation number is irrational. In fact, in the theorem, we proved that the set of rotation numbers of such pairs of AB with trivial centralizer is dense in R minus Q. So this theorem is obtained from a theorem for parabolic maps and the successive perturbation argument. So the result for the parabolic maps is that whenever you have a map of this form, which has a parabolic cycle on the circle, then its centralizer is trivial. So in the rest of the talk, I would like to give ideas about how these theorems are proved. So I guess most of you, and including myself, are more familiar with maps of the holomorphic maps in the plane. So, and there's an analog of this statement for complex rotations that instead I work with those maps. So, if I have a map of this form, e to the 2 pi I alpha z plus big O of z square, defined on a neighborhood of 0, in the same fashion, we can define the centralizer of F. So from now on, I will just work with the analytic centralizer. So these are holomorphic maps, germs of holomorphic maps, which fix 0, and they commute with F. Of course, these also form a group, and you can only, if you like, you can only consider the rotation numbers of these elements, which I denote by G omega of F. This is the asymptotic rotation at 0 of the elements which commute with F. So this is also a subgroup of R over Z. So in this setting, there is a result by Perez-Markov, which says that there exists an F of this form such that the centralizer is uncountable. So this element is not linearizable and has uncountable symmetries. In fact, his example is quite remarkable because it also has symmetries, infinitely many symmetries with rational rotations. So this group is also contains infinitely many rational numbers that are distinct in algebra. And there's no relation between them. And the way Perez-Markov thinks about this problem is that there's this notion of hedgehogs that I don't go too much into details. So whenever you have a map of this form, there is a full a full invariant set, a compact connected fully invariant set, say K, that contains 0 here. And what he sees is that, when you look at the return maps, F to the QNs, they converge to the identity. So when you have this property, there is in fact, the convergence is geometric. So whenever you have such a relation, you can extract some subsequence Fnj's, which converge to some homeomorphisms. Okay, so basically, you take F to the some Qn, you fix some n, and you take the F to the Qn, and then you take a larger n, F to the Q, say m, that is even closer to identity. So you compose F to the Qn with F to the Qm, and so on. And this way, you can build homeomorphisms that they have to commute, the way they are built as limits of these elements. They will be commuting with F. And then he asks, is the maps that you obtain in this form are holomorphic? Yes. So these will be homeomorphism. These will be homeomorphisms which map its hedgehogs to itself, and whether this map is a homeomorphism, whether this extends to a holomorphic map on a neighborhood of the hedgehog is very much related to the geometry of the hedgehog. So it's a rather difficult problem. So we don't take this approach, and we have a very different technique that we give examples of F with trivial centralizers. So this was also left open. For a dense set of alpha in R minus Q, the centralizer of this quadratic map is trivial. So the argument is very similar to the standard family, but I avoided talking about the standard family because of these Arnold tongues and some technicalities that come up. But otherwise, the argument is very similar. So this is obtained from having the same result for quadratic maps with a parabolic fixed point, and then taking a successive perturbation. The way you prove that there are maps that are not linearizable using the fact that parabolic coils are not linearizable. It's similar, but it's a bit more involved. So maybe I should mention at this point that Ecole and Voronin have a very general theory of these parabolic elements. And they show that for a generic holomorphic map with a parabolic fixed point, the centralizer is trivial. So you may wonder why that does not apply to this, and then doing a successive perturbation, you get this result. It's because for this Ecole and Voronin, you need to fix the rotation number. You fix the linear term here, and then for generic values of the higher order terms, you have a trivial centralizer. But to go from here to here, you need to have like a fixed family of nonlinearities, a fixed nonlinearity, and then say that for infinitely many values of rational numbers, you have a trivial centralizer. So it's somehow a little slightly different from this statement, but that is the least you need in order to use this approach to go into this result. So Alexandre Iliad is studying this problem of centralizer for parabolic maps, in more general classes of polynomials and rational functions. So he has some results which extends this to other families. Sometimes, for many classes, he has triviality of the centralizer, and he can basically use the same idea to pass to trivial centralizers for other classes of maps. But there are also classes, and he also obtains classes of maps that have bigger centralizers. So there are higher rank groups also realized, which in the same fashion pass to examples of this type. So I should maybe emphasize here that we're talking about the local centralizers. So these are the local holomorphic maps which commute with this, and the local holomorphic maps which commute with this. if you take global holomorphic maps, that becomes easier. So let me explain, first explain a little bit about this, the result for parabolic fixed points, and then try to explain, how you go from here to here. So the idea, the problem for the parabolic case, so our technique uses Horn maps or parabolic renormalization. If I want to explain the idea in one sentence, so in fact, to many people, I can explain this idea in one sentence, if they're familiar with this notion. So in the theory of renormalization, there is this idea of analyticity improvements. So it basically says that if you start with a holomorphic map with a parabolic fixed point, which is defined on some domain, or it has some structure, or some structure around the parabolic fixed point. If you renormalize it, it is defined on a larger domain, or more about its structure. It goes along the same principle, but so what we show is slightly different, but in the same spirit. It says that if Q sub P over Q, so this is the quadratic map with parabolic fixed point of combinatorial type P over Q. If this guy has a holomorphic symmetry, then the Horn map or the renormalization of the map must have a rotational symmetry. So the symmetry improves under one renormalization. So of course, it is much easier to show that an element does not have a rotational symmetry, because a rotational symmetry is a very strong condition. So I will try to explain this in a very basic fashion. How we get this kind of principle. So let's take the simplest map, Q sub 0, Z plus Z squared, and I want to see what is the Horn map of this map. So this is the Julia set, and there is a basin of attraction inside, and here we have the basin of infinity. So there exists a fundamental domain, which looks like a croissant, which passes through the fixed point at 0. Any point that is inside the basin will tend towards the fixed point and will pass through this croissant. And on the other hand, if I have a point near 0 that goes off to infinity, it will pass through this croissant, the blue croissant. So it's a kind of a fundamental domain for the iterates near that neighborhood. But it's well known that if we identify the edges using the dynamics for any of these croissants, we obtain a round cylinder, a round infinite, bi-infinite cylinder. So there exists a change of coordinate phi sub attracting and the change of coordinate phi sub repelling, which maps the green to the round and the blue to this round object. And from there exists a map H that is going from the top end of the right-hand cylinder to the left-hand cylinder. So if you have a point near the top end, that will correspond to a point in the blue croissant, but near this end of the croissant. And if I've fallen into the basin, if the point is inside the basin of the attraction of the fixed point, after a few iterates, it will come into the green, and we can map it to the left-hand cylinder. So this map, you can see that this is a well-defined continuous map. In fact, it's holomorphic, and it maps the top end of the cylinder to the top end of the cylinder. So we can project that map by the exponential and obtain a map from a neighborhood of 0 to a neighborhood of 0. So 0 corresponds to infinity here and also infinity here. So of course, you can remove, this is a removable singularity, and we obtain this map, a holomorphic map H. So because we know the global dynamics of the map here, one can see that the Horn map or the big H sub Q0 has infinitely many critical points, but all those critical points are mapped to the same critical value. it's basically because there's a single critical point in the basin, and its orbit will pass through the green fundamental domain, which will boil down to a critical value for this map. But whenever you take all these preimages of the critical points, they come and move into the blue. There will be infinitely many of them in the blue, and they all become critical points for this map. So let's see how this picture fits into having a symmetry near zero. So assume that we have a map G that is a germ of a holomorphic map defined near zero, and it commutes with the Q sub zero. You can just use the commutation property to see that G must be of this form. So the leading term is Z plus some B2Z square and so on. So if I look back into this picture, let's say the red circle is where the map G is defined. So if, a priori, the domain of G can be very small, but we can also choose the green and the blue croissants to be small enough to be contained in G. So you just need to do few iterates on this side and then do few backward iterates on the other side. So let me assume that the green and blue are contained in G. So G induces a map on each of these cylinders. So you basically go from this cylinder into the green here. You apply a G. If the croissant was small enough, then its G will be, will be back again in somewhere that you can iterate backward or forward a few times to go back into the green. So maybe I take a point Z here, you map it here, and then you apply a G. It will be somewhere nearby. You iterate a few times by the quadratic map, and then you move back here. And you can do the same on the right hand side. So this map is defined over the whole cylinder, not just on the top end. So you take a point, you come to the blue, you do one iterate, and then apply a G. So there is some analysis to carry out to actually show that this map is defined over the whole cylinder. But once you have a holomorphic map of the cylinder, this has to be very special. So it's a rotation by mu, and the other map is a rotation by some nu. Yes. And the idea is that the mu and nu, these two numbers are the same, and you can read them from the expansion of G. So again, there's some analysis that says, once you're close, if you have picked these fundamental domains close enough to zero, they basically look, they're bounded by round circles. So this becomes a circle asymptotically, and this also becomes, these boundary curves become circle. And the amount that you move on this cylinder will come from this expansion. So it turns out to be B2 over 1. So this 1 is the coefficient of Q0 in the coefficient of Z square in Q0. So once you have the same rotations, this implies that so G here, I can rewrite G as phi sub attracting T sub mu and then phi attracting inverse. So that is G from one hand side. And the G on the other side is also phi repelling T sub mu and then phi repelling inverse. So of course, these descriptions of these two forms, one of them lies on the left-hand side and this one lies on the right-hand side. So G on the right-hand side is this form and G on the left-hand side is this form. But you can propagate this using the dynamics. So if this is true here, you can iterate backward and then iterate this also forward this way. And there will be an open set of intersection. And on this open set, you have the equality. Then you conclude that it must be true over a whole neighborhood of zero. So once I have this relation, I can just move things around and obtain the relation in this form. And you can see from this, this form of H, that in fact this map is H. So this means T sub mu O H is H O T sub mu, which, projecting down here tells me that the Horn map commutes with the rotation by 2 pi I mu. And if I combine it with what I knew from the previous slide, that this Horn map only has a single critical value. And if you have a rigid rotation, that must be a rotation by 2 pi I, an integer value. So mu is an integer number. So once you know mu is integer, you go back to here and say that, if my g in this coordinate is translation by an integer, it must be the same integer iterate of q0. Okay, so fairly simple observation. So you can repeat the same thing for an arbitrary quadratic map with a parabolic fixed point. So there is some preparation to do at the beginning. So the first observation is that if g is commutes with q sub p over q, then g, the derivative of g, is a root of q, is a q root of q root of 1. And then you can choose a j that, a suitable iterate of q of the quadratic map composed with g will become, have derivative 1 at 0. And this is a rather simple thing to do. And then a bit less trivial is that the quadratic map, we know that if we take the q's iterate, because we know the global dynamics, it will have q basins of attractions, and the multiplicity at 0 is q plus 1. An element of this form with derivative 1, which commutes with that map, must also have multiplicity q plus 1 at 0. So we work instead with this map and that map. So they commute, they both have derivative 1 at 0 and the same multiplicity. So here's another picture that you have, now you have like four q is 4 here. You have 4 basins of attractions, and again, repelling and attracting fundamental domains. And in this case, mu and nu that I was talking about in the previous slide become this quantity that comes from these expansions. So once you have the same expansion, you can repeat the same argument basically and say that the Horn map must commute with a rigid rotation, which is not possible again because H has a single critical value. Yes. So this takes care of the whole parabolic case. And the next step is to show that if I take a sequence of p over q's that converges to some irrational value, fast enough, that irrational value, quadratic map, that quadratic map with the corresponding irrational rotation will have a trivial centralized. So this is what I just said. So there's 2 key definitions here. So the first thing is to control the geometry of an arbitrary germ with a single parameter, with a one-dimensional parameter. So if we take this real number R, which is strictly positive, and we say that a holomorphic map G is R good if G is defined on the open ball of radius R, and it maps that ball into the closed disk of radius 1. Yes, so if I have any germ of a holomorphic map, that germ will be R good for some value of R. Yes, because just by continuity, if you take R as small enough, its image will be small, so it will be contained in this. So this notion allows me to write the the space of holomorphic germs as a countable union of these classes of maps. Okay, so you just replace R with 1 over n. So you look at the union of 1 over n good maps, they become all germs. But the good thing about each of these classes is that the space of R good maps forms a closed set. So if I have a sequence of such maps, because they're all defined on the same domain, the limit will be defined on the same domain. And because they're contained in the closed disk, the limiting map will also map into the closed disk. So that's fairly obvious. So this is the first notion. The second notion is a set-valued function that is defined as follows. So now we fix one of these R's, and we consider the following function. So for each P over Q, which is a rational number, C sub R of P over Q is the set of all integers K, such that the quadratic map with parameter P over Q to the K is R good. Yes. So that means I'm collecting all the Ks such that the quadratic map is defined on the disk of radius R and maps that open disk into the disk of radius 1. So note that we're taking all integer values. So there are the positive iterates, and also when I talk about the negative iterates, the backward iterates, I'm taking the branches that are defined near 0. So I want K times taking backward iterates at 0 and saying that that backward iterate also defined on the disk of radius R and maps into the disk of radius 1. So this set-valued function has some nice properties that I will explain in the next few slides. So the first property is that for every P over Q, C sub R of P over Q is a finite set. So C stands for candidates. So we will see why we are talking about this. But so this is an fairly obvious property that anytime you take a fixed quadratic map with a parabolic fixed point, there are only finitely many values of K such that this is R good. This is because basically near 0 there is the repelling direction, and if you iterate some points in the repelling direction, after some K iterates will go off to infinity. Yes. So there is an upper bound on K's, and also for the negative values of K, there are some points near 0 that you take backward and hit the critical point, and you cannot take further pre-images. So that means the inverse branches are not defined for very large values of K. So this is a trivial property, but it's quite important. So the second property of this function is how it depends on rational values. So I've written the second property here, but you don't need to read this. It's easier to see it in the picture. So say, for example, for 1/4, the candidate values for 1/4 are, say, there are only 3 values, 0, 1, and -1. So that means Q sub 1/4 is only R good for 3 of these iterates. And rotation over 4/5 of these values. And then for P over Q, I have these values. And the statement says that, for any P over Q, there exists a neighborhood, as in this picture, that once P prime over Q prime is in that neighborhood, for any rational number in that neighborhood, the candidates will be contained in the set of candidates for P over Q. That means the red is not allowed. So it's a kind of I don't know, you call this upper semi-continuity or something. When you, for rational values, when you're taking limits, the set of candidates will be always smaller than the limiting value. So in this picture, I have used this, this tag R, because these neighborhoods and everything that we talk about here depends on being R good. So implicitly there is this R there. The second property is more technical, So I have written the statement here. There are 6 quantifiers in this statement. So I don't recommend reading it. But again, it's easier to see it in the picture. So take a rational number P over Q and take its value, the set value function C sub P over Q. So there are these integers, say 0, 1, 2, 3, and then -1. The statement says that for any P over Q and for any fixed R, there is this neighborhood such that if I take any irrational number in that neighborhood and take any holomorphic map, which is R good and commutes with Q sub alpha. Yes? So I want to control the rotation numbers of the maps that commute with some Q sub alpha. Yes? So you can take any alpha in that neighborhood and you take the Q sub alpha. If a germ of a holomorphic map commutes with Q sub alpha, its rotation number must be contained in a thin strip near these values. So I basically multiply those values with P over Q. So P over Q, 2P over Q, 3P over Q. The precise statement is that for any epsilon neighborhood of this value, there exists a neighborhood of P over Q such that this holds. Yes. So whenever you commute with one of these elements, your rotation number must be close to one of these values. Yes. And the claim is that these 2 properties, these 3 properties is enough to build my limiting rotation number. So there is a two-dimensional argument to get the limiting value alpha. So let me take a plane which is tagged by 1/2. So this 1/2, as I mentioned earlier, this is the R good property. So this is my R value, and I start with an arbitrary rational number P1 over Q1. From the second property, I know that there exists a neighborhood of P1 over Q1 such that for any rational number in that neighborhood, the candidates for that rational number are contained in the candidates for the rational number P1 over Q1. And the second property, the third property tells me that if this neighborhood is small enough, for any irrational number that I pick here, and any germ that commutes with that irrational number, its rotation number must be close to a multiple of P1 over Q1, and how close is measured by this 1/2. Yes. So the strip of width 1/2 is the orange that you see here. Yes. So just for simplicity, I've assumed that there's just one candidate here. This set contains just one element, say it's 0. And epsilon neighborhood of that is this orange band. And the first property gives me one neighborhood. The second property gives me a neighborhood that works for rational numbers. The third property gives me a neighborhood that works for irrationals. We just take the intersection, and we have this green neighborhood that both of these properties hold. So that is the first sheet. We move to the second sheet. It is tagged with being 1/3 good. So when I talk about 1/3 good, the set of candidates gets larger because we are only required to be 1/3. So now, just for simplicity, now I've taken 2 candidates. So my set valued function contains 2 values for P1 over Q1. And we pick a P2 over Q2 is small enough. So P2 over Q2 is contained in the green neighborhood. And with P2 over Q2, there exists a neighborhood, which is denoted by blue, such that any rational number in P2 over Q2 in that neighborhood has at most 2 candidates. And again, if I take an irrational number in that neighborhood and anything that commutes with that guy, its rotation number will be in these 2 orange bands. Yes. So you can guess what the next step is. You just take the third rational number and the corresponding interval so that these two properties hold. And as you see, the orange bands are getting thinner and thinner. Yes? So we have like 1/4 good, the next one will be 1/5 good, there will be more bands, but they're getting thinner and thinner. So by doing this, I'm going to guarantee that as we move down in the sheets, the rotation number of an element that commutes with some quadratic map will have a rotation number in these thin bands that are collapsing to a single value. And I would like to collapse these orange guys into a multiple of this rotation number, which will become alpha in the limit. Yeah. So that we would conclude that beta minus a multiple of alpha is 0. So of course we can say that what if this Pn over Qn converges to a rational number, and we just conclude that this rational number the map with the rational rotation number will have a trivial centralizer. But the idea is that if you take this sequence Pn over Qn converge to a value that is, the convergence is very fast, you can conclude that the limit must be irrational. So this requires a relation on the successive distances of the rational numbers. So once you have the candidate alpha, you say that, okay, let me start with an arbitrary map G of this form. So it has rotation number beta, which belongs to the centralizer of Q sub alpha. Okay. So of course, G is arbitrary, but there will be an integer L such that G is 1 over L good. So G is 1 over L good. So that means from now on, from that step onward, because all of these numbers, rational numbers, are contained in the neighborhood of PL over QL, because these are becoming a nest, all the eventual rational numbers are contained in that neighborhood. The set of candidates doesn't blow up. So that means after sheet number L all the way to infinity, I have only a finite number of bands that are shrinking, and the beta will belong to one of those bands. And of course, the band is going to shrink to one of these multiples of alpha. So we conclude that beta is an integer times alpha. So from here, you go back to this formula. You see that if G commutes with that Q sub alpha, the leading term is the same as the leading term of Q sub alpha to the K. Because alpha is irrational, K times alpha is irrational, and the commutation tells me that all the coefficients of this G are the same as the corresponding coefficients of Q sub alpha to the K. In fact, G is equal to Q sub alpha to the K. So with this argument, we build this number alpha, and the argument is the way I explained here. It was a bit quick and maybe very technical, but let me say just a few words about how this goes into this argument is implemented for circle maps. So the standard family f sub a b, which is of the form z plus a plus b times sine of 2 pi z, we can easily complexify this, just taking z to be complex number. So again, a and b are real numbers, but b is taken into that interval, so that this reduces to a diffeomorphism on the real line. This maps the real line to the real line. You can project this complex map via this exponential map to the family of maps S sub AB of this form. So these are holomorphic maps from the punctured plane, punctured at 0 or CS star to CS star. And this has been studied in the 90s. It is shown that you can of course see that because the real line projects to the circle, this becomes a circle diffeomorphism, and because this map commutes with the with the z bar, having real coefficients, the map that we have here, which preserves the circle, it commutes with the map W goes to 1 over W bar. So there is basically a reflection. There's a symmetry with respect to the reflection with respect to the circle. So the dynamics of S sub AB and its like parameter space has been studied in the 90s, notably by Nuria and Lucas Gehr. So I'm thankful to Nuria for quickly responding to my emails when studying this problem. So we were very quickly able to show that the same argument works here as well. So there are some differences. So when you take a map of this form, which has a parabolic cycle on T, the Horn map will again have infinitely many critical points, but they are mapped to two values. But these two values will satisfy this relation. They have the same argument. Yes. So in other words, the critical values of the Horn map lie on a ray passing through 0. So if there is a rotational symmetry that maps one critical value to the other critical value, either you have like a single critical value, so that means these V1 and V2 collide at one point, or the rigid rotation will be a dilation, doing an expansion or a contraction. But if there is such a dilation, the Horn map must be defined over the whole complex plane. So you rule that out, and if the V1 and V2 collide, have a single critical value, you just repeat the previous argument that the rotation must be just identity. Yes. So the rest of the argument goes through modulo these Arnold tongues that you need to take into account, but otherwise the argument is of the same technical difficulty. Yes. So maybe I stop here because I'm over time now.
Thank you very much for a very nice talk. Since we're a few minutes over time, any quick questions or comments? So first from the on-site audience.
Any chance for an example in the for maps with Bruno numbers, or would you expect that Bruno numbers always have an uncountable centralizer?
Yeah, so the Bruno numbers always have full centralizer because they, if I understand the question correctly, when you have a Bruno rotation number, the map is conjugate to a linear map, and this linear map commutes with all the other linear maps.
But is it the property of Arman maps, Arman numbers that rotation number is Arman if and only if it's always conjugate to a linear map?
You mean for complex?
Yes, I'm asking about the circle case.
Yeah, for the circle case, yes.
Right.
Yeah. When you have the Hermann condition, you have a full group. But outside the Hermann condition, then there are these examples of uncountable centralizers.
Yeah, but is it possible to construct an example with a trivial centralizer in the Bruno class? So, or would you expect that such example doesn't exist? Sort of what I'm asking is some kind of a little bit worse arithmetic than a good arithmetic that guarantees linearization.
Well, I'm guessing, if I was forced to make a conjecture, I would say that as soon as you leave the Hermann condition, there is always a map which have a trivial centralizer.
Okay, so you don't expect any relation with how bad the arithmetic is. Okay.
Yes. Of course, that's just a guess.
Thank you. let's send to the speaker again. And Peter will make a short announcement for on-site participants.
Yes, I have an announcement about taxes for tomorrow for you. There's a list at the reception. Please